Today we'll discuss a topic called as Laplace transform. Now when you talk about the gate prospect, the marks from this chapter directly in gate would be 0 to 2 marks. If you see the average of the last 10 years papers, normally this is important for electronics students or electrical student when they study for control systems or other technical subjects. But as because it is in our syllabus of engineering mathematics, let us discuss what are Laplace and what are the effects of this Laplace and how to solve question based on Laplace. Now, what one important thing first of all you have to understand why we are discussing Laplace. It is very essential for us to understand why we are discussing Laplace. We are discussing Laplace because sometimes the domain analysis in time, you know, there most of the things are in time domain, you know. So we are changing with respect to time, pressure, volume, whatever we are changing with respect to time. But it is difficult. Some analysis are difficult to analyze. Sometimes, I'm not saying always, sometimes. For some analysis, right? For let's say for some analysis, this is difficult. So what we do is we convert this into frequency domain where we can easily solve this particular thing. Time domain is basically represented by t and frequency domain is represented by s, and that can be done by Laplace transform. This can be done by Laplace transform. Clear? So basically Laplace transform converts time domain signals to frequency domain. Correct? We have got it very clearly, right? So basically Laplace transform's role is to convert time domain to frequency domain, right? Now what is the statement of Laplace transform? Let us discuss that. We'll say Laplace transform, basic definition of Laplace transform is given as let ft be a function of time. This is in time domain. It is let's stop. Assumed it is assumed that the value of the function ft is 0 for t less than 0. That means we are saying that the function do not exist when we are discussing. When we are saying for t less than 0, the function is not existing, right? And we also know that ft is continuous for all t's from 0 to infinity. Then the Laplace transform. Then the Laplace transform. Then the Laplace transform is given of ft is nothing but Laplace of ft. This is the Laplace operator basically is equal to f of s, and mathematically it is represented by 0 to infinity e raised to minus st ft dt. Is very much important for this chapter, right? Where s is the complex frequency, where s is the complex frequency given by s is nothing but sigma plus j omega. Sigma is the real part and omega is the imaginary part, right? Now I want to couple of terms, like for example e raised to minus st is called as the kernel, not military one, kernel of the function, and L is the Laplace transform operator, what we call, right? So this is how it works. Now sometimes we can evaluate a two-sided function. This is basically for a single-sided function. Sometimes for a two-sided functions, the Laplace of ft can be also written as integration minus infinity to infinity. The two-sided function e raised to minus st into ft dt for a two-sided function. For a two-sided ft, so both-sided ft. Clear? Similarly, if you talk about the inverse, so it is very simple. Inverse Laplace. Inverse Laplace is denoted mainly by L inverse. Now this will be converting the frequency domain to time domain. This is frequency domain to time domain, right? And if you want to convert this particular thing, is very simple. You can convert, right? Okay. Let us understand some basic formulas of Laplace. I'll give you the basic idea. Let's say I want the Laplace of ft is equals to 1. Ft is equals to 1. So what will be the Laplace of ft? Laplace of ft will become integration of 0 to infinity e raised to minus st into ft, that is 1 dt or ds dt, right? So integration equal to e raised to minus st upon minus s, limits are from 0 to infinity, it is 1 by minus s. I have taken separately, so it becomes 1 upon e raised to st, limits is 0 to infinity. If I substitute the limit, e raised to infinity will become infinity, which is 0. This is nothing but minus 1 by s of 1 upon infinity minus 1 upon e raised to 0, which will be 1. So it is 1 by s. So we can directly remember this as a result that t in time domain, if I Laplace this, then it will become 1 by s. Clear? Not t, 1. 1 in time domain will be equal to 1 by s in frequency domain. Fine. Similarly, there can be many transformation, right? If you do it for t, in fact, e raised to minus st into t, if you solve it, it will be coming out to be 1 by s square. So I'll give you a list of Laplace transforms. Some standard Laplace transform. What are the standard transforms? Let's say this is function, and I will write down the transform. Function is, let's say, impulse response del of t. Transform is 1. 1 we have just seen 1 by s. If you say t, it is 1 by s square. T raised to n will become n factorial upon s raised to n plus 1. To bifurcate these things very smoothly, then you can have sine omega t. Many functions you will find in sine omega t times, right, is omega upon s square plus omega square. Similarly, when you talk about cos omega t would be s upon s square plus omega square. Then e raised to at is nothing but 1 upon s minus a. Then if it is something like e raised to at into cos omega t, e raised to at into cos omega t, then this would be nothing but shifting. It will happen s minus a upon s minus a the whole square plus omega square. Similarly, if we do e raised to at into sine omega t, so this will be normally sine, what do you write? Omega. So we will keep omega upon s minus a the whole square plus omega square. This is how you can keep this particular thing, right? One important result is we will use gamma function here, t raised to 1 by 2, because for t raised to n, the n should be greater than or equal to 1. So this is directly, you can remember, it is under root of pi upon 2s to the power 3 by 2. You can prove it. We'll use through gamma functions. We can prove this particular thing also. So these are how we can calculate the Laplaces of different standard functions. Right? Now we'll solve a couple of problems so that we can understand how it works. Let's take the question. Find the Laplace of, or the Laplace transform of. So Laplace transform, if you see, of s plus 9 into s square plus 6s plus 13, right? So first let us multiply this. This will become but s cube plus 6s square plus 13s plus 9s square plus 9 6 is 54s plus 117, right? So you want Laplace transform inverse, sorry, not transform, this is inverse. Now inverse also we can do it in the same fashion, right? If we know the Laplace, we can find out the inverse also, right? It is just the opposite of that particular thing. So if you simplify, this will become s cube plus it will become how much? 15s square plus 67s plus 117. This is basically the Laplace, right? Sorry, this is the problem is actually this is divided by, right? So I'm sorry, the problem is actually divided by. So what we will do is we'll find only the denominator factors. So otherwise I will not be able to solve it, because that's what I thought. Okay, how can this be solved? So you want the Laplace inverse of fs. So that will be nothing but s plus 9 upon the denominator can be written as s plus 3 the whole square plus 4, right? So we can say this is nothing but, can I say it is e raised to minus 3t. I can take out, and this is Laplace inverse of s plus 6 upon, so right, s minus, sorry, s plus 4. So this will become how much? Directly we can say now it is e raised to minus 3t. You can separate, right? You can separate this. You can say it is s upon s square plus 4 and plus 6 Laplace inverse of 6 upon s square plus 4. So one will convert to cos and one will convert to sine. It will become e raised to minus 3t into cos 2t. The first part is very simple. Plus 3, you can take common, and you can say it is 3 sine 2t. Right? So this will become your Laplace inverse. Clear? So let us discuss the next agendas of Laplace transforms. See, I'm not getting into the detail of this chapter because in GATE it is not very important, number one, in engineering maths portion. But and you will also study this subject or this topic in your other subjects, in your respective technical subjects also. So I'm just being very much concerned till the Laplace finding out and the inverse of that particular thing. Still, we'll discuss a couple of properties of Laplace here. Properties. Number one property is linearity. Linearity. What does linearity property say? Is that, for example, if I have a Laplace of a function ft, a times ft I have taken, plus b times gt, let's say, right? I have a function like this, or I have a time domain signal like this. I want to find the Laplace. So this can be written as Laplace of a of ft individually plus Laplace of b of gt individually, right? So this is basically the meaning of linearity property. You can prove it very easily. This can be done, right? Substitute everything in your basic definition of Laplace. What was the basic definition of Laplace of ft? Basic definition was, it is nothing but f of s, or we call it integration 0 to infinity e raised to minus st, the kernel, into ft dt. So if you substitute this ft and you will solve it, this is the basics. In any game you say it is stick to the basics. So in gate examination also I will say stick to the basics. Wherever you feel stuck, stick to the basics. You will get your answers. And one more property I would like to discuss here is called as shifting property. Shifting property. What is this shifting property? Let us understand. Let's say if f of t has a Laplace equal to f of s, then Laplace of e raised to atft, if I multiply the signal by e raised to at signal, or maybe whatever you call it the function, then it will be equal Laplace of f of s minus a. How will you prove this thing? It's very easy again. I'll just show you. I have not shown you the proof earlier also. But I'll show you here. Let us prove this. Prove. What I'm saying is Laplace of e raised to at. I'm talking about LHS, left hand side of ft. So from, let's say, basic definition of Laplace, we know that we know that Laplace of f of t, whatever comes under this bracket, is nothing but integration 0 to infinity e raised to minus st into whatever was this in bracket. I'll write it here, ft dt, right? So similarly, when we are talking about when we're talking about Laplace of e raised to at ft, so this is nothing but 0 to infinity e raised to minus st into, instead of this ft, what I will write is, I will write it e raised to at f of dt, right? Now in the this I can write it down 0 to infinity. Can I say, if I take e, this is also e, this is also e, in between you have multiplication sign, so I will take minus s common, so it is s minus a t f of t dt, right? Now what is this expression? I have replaced s with s minus a, so can I say this is nothing but Fourier transform of s minus a, isn't it? Right? So you can see e raised to at f of t has been written as this, so hence proved, right? So easily you can prove this particular type of examples, right? Now you can solve a couple of problems on this particular thing directly or indirectly. You will get the questions, right? Inverse Laplace also we have already discussed how to find out inverse Laplace, right? For example, if I say find inverse Laplace of 1 by s minus a, so it is very simple. It will be nothing but L inverse of 1 upon s minus a. So this is nothing but e raised to at, because I know Laplace of e raised to at is 1 upon s minus a, so that becomes very simple for us to understand, right? Let us solve one question which came in GATE exam in 2010. The question was, find the inverse Laplace transform of the function ft is equals to 1 upon s square into s plus 1. Sorry, this is not ft, it is fs, right? So you need to find out ft, basically find ft. So that is basically later find inverse Laplace transform. Options given to you were t minus 1 plus e raised to minus 1, t plus 1 plus e raised to minus 1, minus 1 plus e raised to minus 1, 2t plus e raised to t. Now when you solve it, you want ft, you basically want ft, right? Now when you talk about ft, so ft is nothing but Laplace inverse of the given module, that is 1 upon s square plus s plus 1, sorry, not plus, into, right? So if I use partial fractions here, we can use partial fractions. Yes, how will it look like? It will be nothing but a upon s plus b upon s square plus c upon s plus a. Now when I solve this, 1 upon s square into s plus a is equal to as into s plus a plus b times s plus a plus c times s square upon s square into s plus a. right? So when we match coefficients, you will find that a plus c is equals to 0, a plus b again comes out to be 0, and directly we can see b is equals to 1. So solving all the given values, what we'll get is a is equals to minus 1, b is equals to 1, and c is equals to 1. So ft basically, now I can recognize ft now, right? Ft will basically become L inverse of minus 1 by s plus 1 by s square plus 1 upon s plus 1, right? So this can be basically written as, now here we can use linearity property. This is minus 1 by s means minus you can take common, so you can say minus 1, sorry, you can individually get the inverse L1 of minus 1 of 1 by s plus Laplace inverse of 1 by s square plus Laplace inverse of 1 by s plus 1, right? So if you get these particular things, you will win the game. How? Let me explain you. So simple, this will 1 by Laplace inverse 1 by s is 1, so it is minus 1 plus t plus e raised to minus t, simply. So if I rearrange according to the options, t minus 1 plus e raised to minus t. Which option? Option A. That is how you could have got a mark in GATE 2010, right? Clear? So these are the types of stuff which can be asked. Now there are 2-3 concepts which are given in your booklets also, but they are not important in terms of engineering maths is concerned. Like convolution. Convolution basically you study in your signal and systems, right? So it is not a topic for mechanical basically. This is for electronics, electrical student, instrumentation students, because that is purely into signal and system. So you'll study that in detail there. So I'm not discussing convolution here, right? Similarly, time shifting, time scaling, nothing has been discussed here. Couple of things which I may mention here is what we have discussed till now is frequency shifting, right? What we shifted was, let us talk about certain things, like we already discussed about this frequency shifting. Now what is this frequency shifting? For example, we have said Laplace of e raised to atft, what it will become? F of s minus a. We shifted the frequency by a. Similarly, if it was Laplace of e raised to minus atft, it would have become f of s plus a, right? Similarly, sometimes you may also encounter something called as time shifting. Just remember these as results. Don't get into the nitty-gritties how they are coming. You will study in your respective subject. I'm just telling you. Sometimes you may encounter t minus, let's say t naught. This is shifting in time domain. So in frequency domain, it will become e raised to minus stfs, because the formulas are just the opposite. Right? This is called as time shifting. If you shift the time, you will have a factor of e raised to minus st. Similarly, differentiation in time domain, what effect it will give? You will see, if I say Laplace of d by dt of ft, d by dt of ft, this is nothing but s times f of s minus f of 0 if there was some initial conditions, right? So I can say that in differentiation in time domain, I am talking about time domain. You say differentiation. So the effect is multiplication by multiply by s in frequency domain. Clear? So this we have to remember, right? Similarly, see, differentiation and integrations are counter effects. So integration effect. So integration in time domain. What is integration in time domain? Laplace of integration of ft dt is going to give you fs by s. So basically this is nothing but integration in time domain. What you can say is again time domain and frequency domain. So in time domain, if you are saying it is integration, so in frequency domain it is giving you a counter effect. That is what it is giving you, divide by s. Clear? So these are certain things which you have to understand, digest, and get it done, right? Then one more thing I would like to discuss here is initial value theorem. Initial value theorem. What is initial value theorem? Let's say if ft and its derivative are Laplace transformable, are Laplace transformable, that means Laplace is possible, right? There are certain functions whose Laplace is not possible, so that is why this condition is mentioned. Then limit t tends to 0, initial condition is 0, ft will be equal to limit, we convert it to s domain, so s tends to infinity. Then if time is 0, s tends to infinity into s of fs. This is called as initial value theorem. This is very important, right? Similarly, you can also have a final value theorem. What is final value theorem? This limit will change to infinity because you are talking about final value. So this limit will change to 0. That is the only change you will find in final value theorem. Clear? And you can have convolution, and you can have periodic functions, Laplace, lot of things. But I'm not getting into the detail. I have already told you I'm not getting into the detail because you will get this thing in your respective subjects.